Hello everyone, my name is Hugh Bin Ta, and I'm excited to present our work titled Low-Rank Adaptation in Multilinear Operator Networks for Security-Preserving Incremental Learning. This paper addresses a critical challenge, enabling AI models to learn new tasks over time while keeping sensitive data secure. In security-sensitive fields like healthcare and finance, data must be encrypted to protect confidentiality. A strong encryption method is leveled fully homomorphic encryption, or LFHE. It allows computations directly on encrypted data, and the results, when decrypted, match what you'd get from computing on the original data, as illustrated in the image below. However, a major limitation of LFHE is that it primarily supports only addition and multiplication operations. Traditional deep neural networks like VITs and CNNs heavily rely on nonlinear activation functions, which are not supported by current LFHE schemes. This means these networks require data to be decrypted for processing, exposing sensitive information and posing a security risk. To overcome this, researchers have developed polynomial networks, which use only operations compatible with LFHE. The state-of-the-art in this family is the Multilinear Operator Network, or MONet. MONet can perform on par with modern architectures in tasks like image recognition while operating correctly on LFHE encrypted data. The core building block of MONet is the mu layer, which relies on learnable channel projections and element-wise products. When MONet computes directly on LFHE encrypted data, the decrypted output is the same as computing on the original data. While MONet solves the encryption, it suffers from catastrophic forgetting in incremental learning settings. Incremental learning is when a model learns a sequence of tasks over time. Catastrophic forgetting is the phenomenon where learning a new task significantly degrades performance on previously learned tasks. Our goal is to enable MONet to learn multiple tasks sequentially while maintaining performance on all learned tasks. Furthermore, in real-world scenarios, the model often doesn't know which task an input belongs to during inference. It needs to be task-agnostic. Crucially, our solution must also adhere to LFHE constraints and ideally work without storing data from previous tasks. This highlights the need for the first security-preserving incremental learning framework. To address these challenges, we propose a new framework, Incremental Learning Framework with Polynomial Low-Rank Adaptation, or LoRA. We developed polynomial low-rank adaptation specifically for MONet, applying low-rank updates to its channel projections. For the task-agnostic incremental learning setting, we concatenate the LoRA parameters learned for each task. The key challenge then becomes preventing the parameters for a new task from interfering with previous tasks. To solve it, we used gradient projection memory, GPM, to mitigate catastrophic forgetting. We proved theoretically that fine-tuning matrix B is functionally equivalent to updating the previous weight matrix within the subspace spanned by the rows of matrix A. GPM helps us initialize the down projection matrix of the LoRA pair such that the subspace for the new task's updates is orthogonal to the gradient spaces of previous tasks. This means training the new task's parameters minimizes interference with the knowledge learned from old tasks. In LoRA, for each new task, we add a new LoRA branch. We initialize the down projection matrix using GPM based on the new task's data and past task gradients, and we only train the up projection matrix. We conducted extensive experiments on popular incremental learning datasets like CIFAR 100, ImageNet R, and PAX. Our results demonstrate that both LoRA variants, LoRA C and LoRA M, significantly outperform baselines like full fine-tuning and classifier fine-tuning, with accuracy improvements often exceeding 17%. Crucially, ablating GPM from LoRA variants resulted in significant performance drops, proving GPM is essential for mitigating catastrophic forgetting. The left figure shows that unlike full fine-tuning, which severely forgets old tasks, LoRA maintains performance much better across all tasks. The right one illustrates that LoRA maintains higher average accuracy throughout the incremental learning process compared to baselines. In addition, the top figure demonstrates that LoRA methods maintain relatively high accuracy as the rank of the projection matrix is reduced, highlighting their parameter efficiency. The bottom table shows that although LoRA M has slightly lower accuracy than LoRA C, it requires significantly fewer additional trainable parameters across different ranks of the projection matrix. In summary, we proposed LoRA, a novel framework combining polynomial low-rank adaptation with gradient projection memory to enable security-preserving incremental learning for MONet. Our method effectively combats catastrophic forgetting while adhering to LFHE constraints, offering the first known solution for continual learning under data encryption.